Hello everyone, I'm Paul and today we're solving problem 1900, the earliest and latest rounds where players compete. There are at least two ways to solve this one, so I will show you both, and given that this is hard, we'll go step by step. So let's start. This is a very long description, but basically we are in a tournament, and in this tournament we have players competing against each other, and we need to return an array with two values. The first one is the earliest possible round in which two given players, first player and second player, compete against each other. And the second value in this array is the latest possible round in which these two players compete against each other. Now there are many things to consider here. Let's say there are 11 players, so n is 11, and let's say first player is 2 and second player is 4. So this is the input. So these are the players, and these players are in a row. We'll use 1 for players that are competing and 0 for players that are not competing. And given that these players are in a row, for example, this is the first player, this is the second player, and this player is in green because this one is special. Remember, we have two values here, first and second. So players in green are special. The fourth player is also special, so it's also in green. Now, these players compete against each other in the following way. The first one competes against the last one. The second one competes against the last one minus 1. The third one competes against the last one minus 2, and so on. And this player in the middle has no one to compete against. So for example, in the match of these and these players, none of these players are special. So we can choose which player wins. So we can transform this one into a 0, or we can transform this one into a 0. Both players can win here. Now if we take a look at this match, for example, here we have one special player, remember these are special players, against one non-special player. And in this match, these special players always win. So in this case, this player wins, meaning we need to transform this into 0. Now whenever we have an odd number of players, such as in this case, we have one player in the middle that's alone. This player automatically advances to the next round. Now let's do a small simulation here. Let's say this player loses, this one wins. Here this one has to win, so this one loses. Let's say this one loses. Here this one has to win, so this one loses. Let's say this one loses, and this one is alone in the middle, so this one automatically advances to the next round. So this was round 1. Now for round 2 we have these players, and now we need to repeat the same process. Player 2 competes against player 11, player 3 competes against 7, and 4 competes against 6. Now we have 6 players, and 6 is an even number, so we don't have this middle player. Now for this match, player 2 has to win, so this one loses. Let's say here player 7 loses, and here this one has to win, so this one loses. So for round 3 we have players 2, 3 and 4. And here player 2 competes against player 4. Remember, these two players are special. And given that we are at round 3 and this happens to be the earliest possible round number in which special players compete against each other, we add to the result at index 0, 3. Remember, this second value is for the latest possible round number in which these special players compete against each other. For this input, the result is 3, 4. Now this sounds tricky, how can we get the earliest possible round number and the latest possible round number in which these players compete? This sounds very hard, but the solution here is in the constraints. We know that the number of players is smaller or equal to 28. So we can run like a simulation here for every possible round in which these special players compete against each other. So in this case, in this simulation, the round is 3. But there's another universe in which the round in which this and this compete is 4. And there might be another universe in which the corresponding round is 3 also. So we can have multiple universes. Let's see what I mean here. Let's say we are back in the starting point. Here this player competes against this player, and if this player wins, if this one loses, here we have one universe. Meaning in the next round we have this player, player 1, which may win or may lose. So here we have branches. If this player loses and this player wins, here we have an entire different universe in which player 11 then can win or can lose and so on. So we have different universes for every match combination. For example, the results for this match could be this or this. So now I think you get the idea. For every result we have a new universe. So we will run a different simulation for every possible universe. And the way to do this is with dynamic programming and DFS. And we are checking in each of these universes when is the time, meaning in which round we have a match of this player against this player. And here we show you two solutions for this. The first one is with bitmasking. For this solution we use 1 for players who are competing and 0 for players who are not competing. This is the main idea for bitmasking. These are the initial players and we have different universes. This is one possibility, we also have this possibility, and we have more possibilities, okay? So if we take player 9, for example, this can win or can lose. For example, here player 9 wins, here player 9 loses. So we'll iterate the first half of the players with an I pointer and the second half of players with a j pointer. So if at some point I is greater or equal to j, we know that we can move to the next round, meaning we have already seen every possible match. Now if we see a match of special players, for example here, let's say the I pointer is here and j pointer is here, when we reach to this match we can return the number of rounds. This is round 1, this is round 2, this is round 3. So in this case we have a match of special players, so we add 3 to the result. Now let's say the I pointer is here and the j pointer is here. In this case, this player has already lost, meaning we need to update the j pointer. Now if we have a match of a special player and a player that's not special, for example here, remember in this case we have only one possible result, meaning this player has to lose. And if we have a match of non-important players, we have a universe in which this one wins, for example, player 3 wins, player 6 loses. We have another universe in which player 6 wins and player 3 loses. So this is basically the idea. We will run simulations for every possible universe, and each time we reach this point where we have special players matching against each other, we add the current round to the result, and finally we return the minimum value here and the maximum value here in a new array. So here the result is 3, 4. So now let's go with the code for this approach, and then I will show you a solution that's more specific for Python. First, we'll say first player is F and second player is S. And we'll say the result is initially an empty set. We are using a set because we can have repeated values here. And we are using self.res because we want to be able to access this variable from the DFS function. And we are working with a Bitmask here. So this goes from index 0, meaning we need to subtract 1 from first player. So first minus equal 1, and we do the same for the second player. Now we can create our DFS function. This will take a mask, a round, an I pointer, and a j pointer. And first we are saying if at some point I is greater or equal to j, we call DFS with the current mask and round plus 1. We are moving to the next round in this case. And the I pointer is 0 again, and the j pointer is n minus 1 again. So we reset everything here. The only difference is we are in the next round. Now, if the player at the I pointer has already lost, meaning it's 0, we need to update the I pointer. So we will say if 1 left shift I bitwise and mask equals 0, meaning if the current I player is 0, we call DFS with mask round, and we need to update the I pointer, so I plus 1, and we keep the j pointer as it is. Similarly, if the player at the j pointer has already lost, we need to update the j pointer. So else if 1 left shift j bitwise and mask, if this is 0, we call DFS with mask round. We keep the I pointer as it is, and we need to update the j pointer, so j minus 1. Now, if the player at the I pointer is the first player, meaning it's special, and the player at the j pointer is the second player, meaning it's also special, we need to add to the result the current round. So if I equals f and j equals s, self.result.add the current round. Else, meaning if we are having a match that's not of two special players, we say the following: if the player I is not special, meaning if not I in fs, we need to open a new universe in which this player at I loses. So we call DFS and we update the mask. So we use bitwise XOR 1 left shift I, and this is a new mask in which the player at I is 0, meaning it loses. We keep the same round, and we need to update both players for the new match. So I plus 1 and j minus 1. Now similarly, if player j is not special, meaning if not j in fs, we call DFS and we need to change the mask. We need to make player j lose. We need to transform it from 1 to 0. So mask bitwise XOR 1 left shift j we keep the same round and we update both pointers. So I plus 1, j minus 1. Now we can call the fs with a brand new mask. So we do 1 left shift n and we subtract 1. This is how we create the mask. And we start from round 1. The I pointer is 0 initially, and the j pointer is at n minus 1 initially. Now remember, we are working with binary here, and binary reads from right to left. So the position 0 in binary is to the right. And now we need to do this to avoid memory limit exceeded in Python, which is the following. We do dfs.cache clear, and here we need to cache this, meaning we are storing every possible state, meaning every combination of mask, round, I, and j pointers. And we do this to avoid MLE. And now we have all the information we need in our set in the result. So we need to return an array with the minimum value in the result and the maximum value. So this is it for the code. Now let's submit this and see if it works. And as you can see, this works. Time complexity for this will be roughly big O of n times n times 2 to the power of n. And space complexity is roughly the same, because we are caching this. Now I will show you a second solution that's more specific for Python. Now instead of having an I pointer and a j pointer and a mask and rounds and players, we are just having rounds and players. So we don't have all of this. We start from these players, and here we have one possible outcome. Here we have another possible outcome. Remember, we have more possible universes. And the idea is basically the same as before. From these matches we can have this outcome, and here we have two special players facing each other. So we add the current round to our list of values for the result. Remember, from here we take the minimum, the maximum values, and we return this. And for this approach we can use a Python function product. So let's see how this function works. Let's say we are at round 1, and these are the matches in which we have no special players. For example, 1 has a match against 11. In here we have 1, 11. So initially we had 3 matches without special players. So there might be a case in which the winners here are 1, 3, and 5, for example. There might be another case in which the winners are 1, 3, and 7. So from these 3 matches we have these 8 combinations of possible winners. And each of these combinations is a different range here. For example, 11, 3, 5 is what we are using here. And we need to test all of these branches. So at each step we take the possible winners, let's say we take this, and we need to add the special players, meaning 2 and 4, and the player in the middle if we have an odd number of players. So for example, here we have 11, 3, and 5. We also have 2 special players, and we have the player in the middle, which was here, 6. So we repeat the same process with these players, and we reach to some universe at some point, which is this one. And here player 2 is facing player 4. So we add the current round to the result, to our set, and after we gather all the information from all the possible universes, we return the minimum and maximum values from the result. So now let's go with the code for this approach, and hopefully you will get the idea. First we'll say first player is F, second player is S. And the result is initially an empty set, so self.res is an empty set. Remember, we are using self because we want to be able to use this inside the DFS function. So now we can create the function. We'll call this DFS, and this takes players and round. First, n is the length of players, and we will use a variable, we'll call this pairs, and here we will store every match, and every match of non-important players. This is initially empty. Now for I in range n divided by 2, the player A is players at I. Player B is players at n minus 1 minus I. And now if A is the special first player and B is the second player, remember here we need to add to a result the current round. So self.res.add round, and we return. Now if player A is not important and player B is not important, we can add this match to pairs. So if not A in FS, not B in FS, pairs dot append, and here we add a tuple with A and B. Now we have some players who are passing to the next round. For example, special players who have a match against non-special players. And we also need to consider the player in the middle for when we have an odd number of players. So we'll call this to add. These are the players that we need to move to the next round no matter what. So we need to move the two special players, this is for sure, and we will only move this if n multiplied by 2 is 0. Else we need to move first, second, and players at n divided by 2. And it might be a case in which the player in the middle is the special first player or the special second player, and we don't want to repeat players. So we can use a set. This is how we avoid duplicates. We are working with tuples, so we transform this into a tuple. And to use set here, we need to use an array. So now we can move to the next part. This is key for this approach. We'll say for winners in product, and here we need to unpack pairs. Remember this function we saw minutes ago. This will give us all the combinations of winners, and from this we can say the next round will include winners plus the players to add. And remember, we always need to keep sorted order, so we use sorted here. And now we can call DFS, and for players we are using tuples. Here we put next, and we move to the next round, so round plus 1. Remember, we are using tuples here, and this is very important. We are also caching this DFS function, so tuples are very important here. Finally, we can call DFS with a tuple, and this will include the initial players. So we can say x for x in range from 1 up to n plus 1, and we start from round 1. Finally, we need to return the maximum and minimum values in the result. First is the minimum value, so min self.res and max self.res. And now finally, remember we need to cache this. So here we get the word cache, and we are storing every possible state of players and rounds. And now this, I think this is right. So let's submit this and see if it works. Here I'm missing an S, so let's fix this and try again. And here I'm missing an L, so let's fix this and try again. As you can see, this works and it's much more efficient than the previous solution. Time complexity for this will be roughly big O of 2 to the power of n, and space complexity is the same because we are caching this. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.